Now, over 15 billion miles away from Earth, humanity's farthest outpost is flying through the absolute dark of interstellar space. To stay alive, Voyager 1 relies on a radioisotope thermoelectric generator. It converts the heat from a decaying lump of plutonium into the electricity that powers every onboard system. This chart shows the unavoidable math of that nuclear decay. Every year since its launch in 1977, Voyager 1 has lost about 4 watts of total electrical capacity. The probe is slowly freezing. Its continued survival requires a ruthless game of resource management, shutting down secondary systems to keep the vital hardware warm. On February 27, 2026, during a planned roll maneuver, Voyager 1 experienced a sudden, unexpected drop in its limited power reserves. That dip pushed the spacecraft dangerously close to triggering its undervoltage fault protection system. This logic schematic shows how a critical power drop forces a hard, automatic shutdown of multiple components. It is a last-ditch effort to protect the central computer from a complete brownout. Triggering that defense mechanism is a potential death sentence. At this distance, a cold reboot carries the massive risk that frozen fuel lines or 50-year-old computers will never wake up. Engineers at NASA's Jet Propulsion Laboratory had to act before the fault protection took over. To prevent a hard crash of the entire spacecraft, they decided to intentionally amputate one of its functioning sensory organs. This diagram shows the chosen sacrifice, the Low-Energy Charged Particles Experiment, or LECP. It has been running almost continuously for 49 years. The LECP acts as the probe's primary tool for tasting the deep space environment, measuring the ions, electrons, and cosmic rays flowing through the galaxy. It is the instrument that detected depressure waves, proving Voyager 1 had successfully pierced the heliosphere and entered interstellar space. Silencing it permanently blinds us to shifts in particle density in this region of space, a region no other active craft can reach. The shutdown command was officially broadcast from Earth on April 17, 2026. This animation illustrates the physics of the mission. Traveling at the speed of light, the signal takes 23 hours just to reach the spacecraft. Once the signal arrives, the physical shutdown process on the probe takes an additional 3 hours and 15 minutes to complete. Mission managers noted that shutting down a science instrument is never a preference, but it was the only viable choice to save the core mission. The April execution stabilized the power grid and stopped the immediate electrical drain, but at the cost of an irreplaceable scientific tool. The energy saved by the LECP shutdown provides Voyager 1 with approximately 1 additional year of operational life. Only 2 science instruments remain active, listening for plasma waves and measuring magnetic fields. Engineers are now preparing a power-saving strategy called the Big Bang. They plan to replace multiple power-heavy components simultaneously to find enough hidden efficiency to keep the probe warm. This maneuver is so risky that it will be tested on the slightly healthier Voyager 2 in May and June of 2026, before it is attempted on Voyager 1. NASA is currently running a high-stakes experiment in how to keep 1970s hardware functioning billions of miles from the sun. The shutdown command broadcast on April 17th left one tiny component of the LECP active. A small motor drawing only half a watt of power was left to continually rotate the dormant sensor in the dark. Keeping the motor active provides just enough heat to prevent the mechanical mechanisms from freezing. If the Big Bang strategy creates a power surplus later, the instrument could potentially be restarted. This is the Voyager Golden Record, a scratched artifact of gold and steel, carrying the memories of Earth deeper into the void. As the data streams of the past 50 years go quiet, that half-watt motor remains, a stubborn, rhythmic pulse of human survival against the dark. In April 2026, NASA engineers sent a final command to silence the low-energy charged particles experiment on Voyager 1. This wasn't a fix. Voyager's nuclear battery bleeds 4 watts of power yearly. Its lifeblood is draining. Without electricity for heaters, Voyager's fuel lines risk freezing, triggering a fault protection survival mode notoriously difficult to recover from at this distance. Silencing the particle experiment didn't rescue the mission. It simply bought the engineering team a few more months to solve a life-threatening energy deficit. The rescue is complicated by a distance that is hard to visualize. Voyager 1 is currently 15 billion miles away from Earth. A radio signal traveling at the speed of light takes 23 hours to reach the probe, and another 23 hours for the confirmation to return to our antennas. This 46-hour round trip means every command is sent in total silence. Engineers transmit a fix and then wait 2 full days to see if the spacecraft is still alive to answer. The sheer scale of this communication lag turns standard engineering into a high-stakes asynchronous crisis. A single typo in a command string could silence the spacecraft forever, long before anyone at JPL even knows it's in trouble. Re-engineering a piece of hardware from the 1970s requires a massive ground-based effort involving some of NASA's most advanced cleanroom facilities. The team has developed a high-risk recovery protocol called Project Big Bang, a plan designed to wring 1 more year of science out of the probe. The core plan is an aggressive power swap. Turning off non-essential heaters lets engineers reroute electricity to keep critical plasma and magnetic field sensors running. To keep science alive, massive sections of internal circuitry must drop to the temperature of the surrounding void. Project Big Bang is a zero-sum trade of watts for warmth. Keeping the scientific instruments active requires letting the rest of the spacecraft drop toward absolute zero. Because of the 2-day communication delay, executing this plan on Voyager 1 first could be fatal. If the power swap fails, the probe will freeze before Earth can send a countercommand. Instead, NASA will use Voyager 2, the identical twin launched alongside it, as a testbed for the Big Bang protocol. Voyager 2 is slightly closer to Earth and possesses a larger power reserve. This makes it the safer candidate for an experimental power cycling maneuver. The tests are scheduled for May and June of 2026. Only if Voyager 2 survives the shutdown will the team send the same instructions to Voyager 1 in July. Voyager 2 is effectively acting as a cosmic crash test dummy, absorbing the risk so its more distant sibling might continue its mission. The immediate goal of this triage is simple: keep Voyager 1 functional until July 2027. That date marks 50 years of continuous operation in space. It is a milestone no other human-made object has ever approached. Even with its particle instrument silenced, the probe is still transmitting data. It is currently our only way to measure the magnetic intensity of the interstellar medium. There is even a chance for a recovery. Engineers left a tiny half-watt motor spinning on the silenced instrument, keeping the mechanism warm enough that it might be restarted if a new power source is ever found. Right now, engineers are performing remote life support on a nuclear-powered machine built half a century ago, floating billions of miles away in the dark. After 5 decades in flight, Voyager 1 is still proving that a machine from the 1970s can adapt to the edge of the galaxy. It continues to drift into the silence, recording the magnetic signature of a new star system for a world it left behind a lifetime ago.